So, good afternoon, ladies and gentlemen. And as you know, we are today the second day of the Eid al-Kabir or Eid al-Adha. So I wish you all the best. So today I would like to introduce distinguished guest, key speaker. It's Professor Dr. Evan Gordon. He's the editor-in-chief for Solar Energy Material and Solar Cell, and I guess you know that journal is a very important journal for us. And he obtained his PhD in the field of novel magnetic materials for sensors application from the University of Leuven in Belgium in 2002. He started to work in the field of photovoltaic in June 2003 at EMIC. Currently, he is the leading of the lab in EMIC and Heselt University. Next to this, he is also professor in digital photovoltaic at Delft University of Technology in the Netherlands. And as I told you, he's the editor-in-chief of the International Scientific Journal Solar Energy Material and Solar Cell, a journal with a high impact factor of 7.3, actually. Since January 2016, he's the coordinator of the joint program on photovoltaic in the European Energy Research Alliance, EERA, and the steering committee member of the European Technology and Innovation Platform Photovoltaics. He will talk about sustainable silicon photovoltaic cell and module technology for the Terawatt era. I want to thank him for having the time for us to give this talk. And Professor Gordon, the floor is yours. Thank you very much.
Okay, thank you very much, Ahmed, for the introduction. And of course, it's my pleasure also to talk to you today about silicon photovoltaic, solar cell and module technology. So yeah, it's something that I've been working on for more than 20 years now. And yeah, as you know, renewable energies are really becoming more and more important, and especially solar cells are really one of the key building blocks of the future energy system. But there are still quite some challenges, especially challenges related to having sustainable manufacturing of these solar cells, as I will explain, because we will need to produce and install a huge amount of solar modules in the coming years and decades. And that's really going to be a challenge, as I will try to explain in my presentation today. So, we know that the world is finally slowly moving towards a sustainable energy future, and we want to become climate neutral, as they call it, by, let's say, 2050. That means that by then we should not really produce any more CO2 in the atmosphere than we have at that moment. And to achieve that, of course, renewable energies are the keystone, and especially wind energy and solar energy will be really very important and the key building blocks. And we see also already today that most of the investments in energy field are going to indeed wind and solar and other renewable energy sources. And why is it happening now? Well, this transition, which is ongoing, is really happening at the moment because, of course, of the cost, which has decreased substantially over the last years and decades. So if we look to photovoltaic solar energy, I show here a curve. This is a so-called learning curve of silicon photovoltaics. It shows you actually with data starting in 1976, the evolution of the cost or the price of PV modules. So the data starts in 1976. So if in the late 70s you wanted to buy PV modules, then you would have to pay $100 per watt of these modules. So it's a very large cost. So for instance, that means if you would have 3 kilowatt system, 3000 watts of modules, you would have to pay $300,000. So it's really huge. Luckily today, of course, the situation is completely different. Today, the average cost for a PV module is only 23 cents per watt peak on average. So that means there is a difference of almost a factor of 1,000 between 45 years ago and now. And of course, as a result of that, what we see also is that the amount of PV modules that are being produced each year and being installed worldwide is also increasing very rapidly. So in 2022, here in this graph, we can see that we installed worldwide in 1 year time, roughly 250,000 megawatts, so 250 gigawatts of PV modules. And that's of course driven by the cost. And these large volumes and the cost reduction, they go hand in hand. So we have seen here that the cost is reduced by a factor of 1,000 over the last decades. Where is this coming from? It's coming on the one hand, of course, because we have technology improvements that make the PV modules more efficient and cheaper. But it also comes from a big part because of the fact that we have a huge upscaling. So the more we produce of something, the less expensive it typically becomes. So before we go on, I just wanted to also put one slide here to make sure that we all talk about the same thing. So in my talk today, I will talk about photovoltaics. So photovoltaic solar energy, that is actually the direct conversion of light into electricity. And here, this schematic simple picture shows a little bit the principle behind how these solar cells and modules work. So you have a solar module, the light is entering into the device and gets absorbed. That is step one here. And it creates electron hole pairs. So the red are the electrons, the white circles are the holes. And these electron hole pairs, once they are created in the semiconductor material, they can travel around. What we don't want is that the electron and the hole, at some point, they recombine again. So this is what we try to avoid as much as possible, this step two. On the contrary, what we want to achieve is we want to collect the electrons and the holes at different sides of the device. So we have two polarities in the device, an N polarity and a P polarity, so negative and positive. And in the best case, the electron hole pairs that are generated by the absorbed light, they are collected in these two contacts. And in this way, an electrical current is flowing and we get a voltage, and so we get power. So basically we convert directly the sunlight into electricity. Now, this technology has become now very successful. And if we look in this graph, we see actually as a function of the years, the cumulative amount of PV modules that have been installed worldwide. And in 2022, we actually achieved a kind of a milestone. For the first time worldwide, there were more than 1 terawatt of PV modules installed. So 1 terawatt is 1,000 gigawatt. It means 1 million megawatt. So we see that at the end of 2022, worldwide, around 1.2 terawatt of PV modules were installed. And this is, of course, the sum of all the PV modules that have been installed over the whole world across all the years. But if we look at the evolution of this number, we see that, of course, most of these PV modules have been installed in the last 10 years. So if you look at 2012, for instance, 10 years ago, the total amount of PV installed until then was below 200 gigawatts, whereas now in 1 year, we install actually more than that. So the total amount of installations is ramping up very rapidly, because of course of the low cost, and because of this up ramping, the cost is even going to further reduce. Now, if you look at the technology behind these PV modules, most of these modules are actually based on what we call crystalline silicon technology. And so that will be the focus of my talk here. So you see here in dark blue and light blue, you see the share of silicon technology in the PV modules. And this is really dominating. It has dominated over the years. And we can say that currently around 95% of the PV modules that are being produced and sold are based on crystalline silicon. And only 5% is based on something else. We call it in general thin film photovoltaics. And this situation has evolved over time, but more or less we can say that the silicon PV has always more or less dominated. So I will explain step by step what is going on in crystalline silicon photovoltaics in the remainder of the talk. I will not focus on the thin film PV, but I will say a few words about it now. So if you look to these 5% of PV panels which are not based on crystalline silicon, they are based on a different material, and there are different materials out there. But most of these thin film PV panels at the moment, they are based on the material cadmium telluride. So that's a compound semiconductor that is being used. It's mostly produced in the United States by one single company actually called First Solar. And yeah, this technology is also quite successful. But of course, it's based on two elements, cadmium, which is a toxic element, but especially tellurium, it's a quite scarce element. So, so that's probably also the reason why cadmium telluride will never be able to be produced in the same amounts as silicon, because it's actually quite scarce. Then there are some other technologies in the market. We have technologies based on amorphous silicon, but that is not really produced so much anymore at the moment because the efficiencies are too low. And you also have a technology based on copper, indium, gallium deselenide, where also several companies are still producing it today. And then there is a new upcoming technology called perovskites, which I will also discuss later on in my presentation. But so in this presentation, I really focus on the mainstream technology, which is crystalline silicon photovoltaics. And when we talk about crystalline silicon photovoltaics, we actually mean the PV panels are based on the use of crystalline silicon wafers as the absorber material. And then we can roughly, if we look at the value chain of crystalline silicon, if you look how we start from sand, which contains silicon, and we can produce a silicon PV panel, we can roughly distinguish 5 steps, which are listed here and which I will explain in the following parts. So the first step is actually to go from sand, which contains silicon, but is unpure, to having actually very pure crystalline silicon. So that's the first step. We make polysilicon. So these are, let's say, chunks of crystalline silicon, very pure, that we have. And then in a second step, these chunks are molten and recrystallized in the form of ingots. These ingots are simply very large and heavy blocks of very pure crystalline silicon material. These ingots are then sawn into individual wafers. The individual wafers are processed into individual silicon solar cells. And then finally, these individual silicon solar cells, they are interconnected and they are laminated into the silicon PV module. And traditionally, 2 types of silicon have been used, 2 types of wafers have been used. We have monocrystalline silicon wafers, where the wafer, the whole of the wafer has only one crystal orientation, so it's one large single crystal. And with this, you can reach very high efficiencies because it's a very pure material with not a lot of defects. But we also in the past were using so-called multicrystalline silicon wafers. So these are wafers where the wafer has different crystallographic orientations. So that means you have different grains of different orientations, some grain boundaries. And typically you also have more defects in this material. But it was used a lot in the past because we could make these multicrystalline silicon wafers cheaper than the monocrystalline silicon wafers. And therefore, it also made sense to use those. But I will show later that at this moment, almost no multicrystalline silicon is used anymore. So then we can have a look at the cost structure of these modules. So I mentioned in the beginning that at the moment, if you buy a silicon PV module, on average, it will cost you 23 cents per watt peak. So where does the 23 cents come from? So of course, you see here in this graph that over the years, the cost of the PV modules has reduced. But actually, in the last year or two, we also see a little bit an increase that has to do with the huge inflation and the problems with the supply chain that we faced because of COVID and because of the war in Ukraine. And if we look now to this inset, so this is for the end of 2022, we see that of this 23 cents, around 40% of this cost is directly related to the polysilicon that we are using. So actually, the silicon material, which needs to be very pure and needs to be, the wafers need to be like almost defect-free. To achieve that, we really already have to, pay a high cost. So around 40% of the total module cost simply already comes from this silicon material itself. Then another 40% is coming actually from the module processing, so to make the module, and especially from the module materials, like, for instance, the encapsulation, the glass, the backsheet. And only less than 20% is actually of the cost is actually related to the cell processing. So we can say that the module cost is really dominated by material costs for the polysilicon, especially, and also for the module level materials that we are using. Now, it's important here to make a remark. We're talking here about the cost of the modules. If you're going to make a PV system, you need more than modules alone. You also need an inverter, you need cabling, you need mounting structure, etc. So everything that you need, which is not part of the modules, is called the balance of system. And if we look to the current cost of a system at this moment, so in 2023, the cost of the modules is only around 1/3 of the total system cost. And so you have 23 cents for the module per watt peak, but you need to add twice as much for the rest of the system per watt peak. And that's very important to keep in mind. And this is a prediction from the ITR PV roadmap. So you will see a lot of images from ITR PV roadmap appearing. So the ITR PV roadmap is a roadmap that is yearly made by the silicon PV industry itself, in which they actually state what is the situation today, and they predict based on their information and how they see the industry evolving. They predict how things will evolve in the next 10 years. So here the prediction is that is dark blue, which is the percentage of the total cost of the system that is in the modules, that it will even further decrease to even below 25%. And this is very important because typically the balance of system cost scales inversely with the efficiency of the modules. So if you have higher efficiency for your PV modules, then relatively speaking, the balance of system cost will be lower. So the fact that the balance of system cost is really much higher, is dominating the total cost, means that there is a big pressure for using as high efficiency modules as possible to reduce the total system cost. Now, I have a few slides where I will show that there are some important things now that we have to investigate in research and development for silicon photovoltaic. So in the past years and decades, most research and development for silicon PV was focused on further increasing the efficiency of the devices and lowering the cost. And that, of course, still stays important. But at present, we can already say that solar electricity is the cheapest electricity out there. So we already are doing very well. We can further improve it, but it's not the only thing on which we should focus anymore. So what is also important, first of all, is that we actually try to increase the operation lifetime of the modules further. So currently, if you buy a PV system, you typically get a 20 or 25 years operational lifetime warranty. But this is probably, we need to further increase this probably to 30 to 40 years even. And so each PV module that you install will have a certain degradation year after year. And it's very important to minimize the degradation rate. And this is becoming now also a very important field of study, especially because PV modules are used everywhere in the world under completely different climatic conditions. So if you use the same PV module in Belgium, where I'm now at, or you use it in Morocco, for instance, it will see a completely different climate during its lifetime. So you really have to tune the technology for the location and the application that you use it for. Then secondly, we really have to focus on sustainable manufacturing. And this will come back later in my story, because we will need to install a huge amount of PV modules in the coming decades. And of course, at some point, all these modules will become too old. We will stop using them. So then also we need to be able to, first of all, recycle them. We can already recycle PV modules, but we can still make a lot of progress there if we also really design the PV modules from the start for easy recyclability. Secondly, when we talk about sustainable manufacturing, we should also look at how much energy do we need to produce the modules and how much greenhouse gas emissions are we making. Because again, we're going to have to produce a huge amount of these PV modules. So if we can reduce even by a few percent the greenhouse gas emission, it can have a huge impact. Now, where does most of the energy come from, or where is the most of the energy needed for? That's again actually in making the polysilicon and the wafers. So we already saw before that the silicon material itself is already representing 40% of the module cost. But if we look at the energy demand for making a silicon PV module, we see that around 2/3 of the energy that is needed is really coming from the polysilicon and the wafer production. So there we also still need to make big progress to reduce this, so that we will also have less greenhouse gas emissions. But I will come back to that later. And then finally, since we are going to install a very large amount of PV systems, we also see a lot of new applications appearing, because of course, traditionally we are placing PV systems on a roof of a house, or we put it in a large PV system. We put it somewhere in a large field. But we might not have enough space. For instance, in Western Europe, we don't have a lot of free space, so we don't always have the space to put large PV systems. That's why we actually see more and more so-called integrated PV applications appearing. So in integrated PV applications, the PV system is really seamlessly integrated into its environment. And that can be in the building, so not just on the roof of a building, but it can be the roof of the building, or it can be in the facade of the building. We can integrate it in the electrical cars that we will all have in the future. We can integrate it in roads or along roads, in sound barriers, for instance. And we also see floating PV systems appearing, so on water. And what is also something which is investigated a lot, especially also in Europe, is what we call agrivoltaic. So it's the combination of agriculture and photovoltaics, where we actually use agricultural land to produce energy, but at the same time also to have crops or even animals that use the same amount of land. So basically we have dual use of the land, and that's really good. Now it's clear for all these new applications, you also have to fine-tune the PV technology, because PV systems in these different environments, they will see completely different conditions. So for instance, if you have PV in a car, the car will move, so you will have much more dynamic shadowing. If you have PV integrated in the facade of a building, it's possible that this PV system becomes much warmer than when it's on top of a roof. So in all these cases, you have to really fine-tune the technology for the optimal performance of these new systems. So that was a little bit an introduction. So now in the next parts, I will first walk you through the whole value chain. So we will have a look at how typically the wafers are made for the silicon photovoltaics. Then we will have a look on how we can make these wafers into solar cells. And finally, we see how the solar cells are assembled together into a module. And then at the end, I will tell you a little bit about the future, let's say, of silicon photovoltaics, where we will go to tandem technology. And finally, I will also highlight a few of the challenges that we have for the upscaling towards terawatt scale production of PV. and how, what are the challenges there to do that in a sustainable way. But first, we will start with the silicon wafer formation. So that's basically the first step in the value chain. And we know that silicon is a very abundant material. So it's the second most abundant material in the Earth's crust. Basically, you find silicon in sand. But how can you go from the silicon that we find in sand into a crystalline silicon wafer that you can use for a highly efficient solar cell? So there are many steps that we have to go through. And so typically from sand, people can quite easily make what is called metallurgical grade silicon. So this is actually silicon which has a purity of, let's say, 98%. So it's already pretty pure, but it's not pure enough for electronic applications, and definitely not pure enough for photovoltaics. So we have to make it actually more pure. We have to go to electronic grade silicon. And this is typically done by making the silicon into a gas. And then we can purify that gas. And you have different silicon containing gases. Here I give the example of TCS, that stands for trichlorosilane. That's one of the most commonly used silicon containing gases. So this is the starting point. We have a very pure silicon containing gas, but now we have to make this into a silicon wafer. So we need many steps actually to do that. So the first step is to make the polysilicon material. So this is done by taking a so-called, well, in the standard way, by taking a so-called Siemens reactor. So you see the Siemens reactor here from the outside, and this is actually a schematic of how it looks inside. So basically in this reactor, you can heat up the walls to high temperatures, typically above 1000 degrees. And you can inject then this TCS gas. And then you will actually have these crystalline silicon rods being grown. So you see them here. So we grow actually a polycrystalline silicon material that is very pure, using this silicon containing gases and also some hydrogen. Now, because we have to heat up the reactor to very high temperatures, it's a very energy intensive process, which is already one of the processes that explains why we need so much energy and why it's so costly to make this polysilicon material. So typically in the Siemens reactor, you need around 100 kilowatt hour per kilogram of silicon material that you make. That's why there are alternatives being investigated already for quite some time, where you use slightly different processes or slightly different reactors, where you can actually reduce this amount of energy per kilogram. So this is one of the important things that we have to work on. We really have to lower the energy that we need per kilogram of silicon that we use. So in the end, in this first step, the so-called Siemens process, we go from gas phase, we go to actually polysilicon rods. Now, these polysilicon rods are not yet wafers, so we cannot use these rods to make solar cells. So typically what is done, these polysilicon rods, they are crunched into small parts, which are shown here. And then we go to the next step, which is we are going to melt these polysilicon pieces, and we are going to grow an ingot. So here I will focus on monocrystalline silicon, and for making monocrystalline silicon ingots and wafers, typically the Czochralski process is used. That is demonstrated here. So in the end, so we start from this polysilicon material, and in the end we end up with this kind of monocrystalline silicon ingots. So how does it work? Again, we have a reactor. In this case, we have to heat it up even higher to temperatures above 1400 degrees, which is the melting point of silicon. And we put a crucible, typically from graphite or quartz, into this reactor. And the crucible is filled with these polysilicon rods that we have grown in the step before. So we heat up these crucibles to more than 1400 degrees so that the silicon is in the molten state. And then we put on top of this molten silicon, we put just above it a small silicon seed crystal. So this is actually a small silicon crystal that has a perfect crystallographic orientation. And by slowly pulling this silicon seed upwards, it actually pushes or pulls some of the molten silicon from the crucible with it, Once the silicon comes out of the crucible, it cools and it starts to solidify, crystallize, and it actually copies the crystal structure of the silicon seed. And this is a very slow process. So by doing this under the right conditions and slowly pulling the silicon seed crystal higher and higher, we actually pull a whole ingot, which can be a very large and heavy piece of monocrystalline silicon out of this melt. Needless to say, again, because we have to use these very high temperatures and it's a very slow process, this is a very energy intensive process, which again explains where or explains the reason why we need so much energy and why it is quite costly to make these silicon wafers. So now we have very large blocks of monocrystalline silicon, very pure, with a certain dopant profile inside that we can control. We still don't have wafers. So how are the wafers now made? Well, these blocks are actually cut into individual wafers by so-called wire sawing. So this is shown here. So these days, already for many years, the wires that are used are diamond-coated metal wires. So basically, you have very small diamond materials, which are actually what cut the silicon. And this wire is very long. It can be kilometers long. And you have special machines where these wires are actually in parallel cutting a whole ingot into individual wafers. Now, the problem with this process is that it leads to a lot of silicon kerf losses. So we lose part of the ingot. Why is that? These wires, they have a certain dimension. Typically, they are, let's say, around 80 to 100 micrometer in width. We cannot make them too thin because then the wire can actually easily break, which is not what you want to have. And so these wires are cutting through the silicon, but everywhere where they cut, basically they pulverize the silicon ingot. So you typically have, after the cutting, you have the wafer, which has a certain thickness, which is determined by the distance between two wires. So typically the wafers used in industry are around 180 micrometers in thickness. But you also have, where the wire was cutting, you have typically around 100 micrometer of silicon that you lose in the form of kerf losses. So after all these steps, we finally have then wafers that are high quality and which can be used to make solar cells and in the end to make modules. So if we summarize this, we can say that this typical way of making the silicon wafers is actually involving a lot of energy intensive and expensive processes. And on top of that, we also lose actually a large percentage of the ingots again during that wafering. And so all of this is responsible for the fact that the energy payback time and the CO2 footprint of the silicon photovoltaics is still relatively high. And it also explains why the cost of the silicon PV module is 40% dependent on the wafer cost. So there is still lots of room for improvement here. Now I will go to a few of the recent developments in these silicon wafers used for photovoltaics. So the first development, which took place very quickly in the last 2-3 years, is actually that the wafer size has increased a lot. So I would call it big is beautiful somehow. So for 10 to 15 years, the silicon wafers that were used in the PV industry, they had always the same size. They were square wafers or semi-square wafers of 6-inch length. So more or less what you see here. So you had a square wafer and the sides of the square were around 156 millimeter. But then because of there were two reasons why the wafer size has increased. There have been actually quite some improvements in the whole process that I just explained, so that it was possible to make larger wafers. And these larger wafers, these larger ingots, typically also reduce the cost. So it's really from a cost perspective that people have started making larger wafers. And you see that the sizes that are now being used are actually going from the original size, 156 millimeter, but all the way to square wafers, which we call G12, of 210 times 210 millimeter. So if you look at the area of such a wafer, it's 80% larger than the original wafers that we used to use. And if we look again to the ITR-PV roadmap, to the present situation, we see actually today, 2022, 2023, that actually different sizes are being used by the industry. So there is not one standard at the moment, but almost nobody is still using the very small wafers anymore. So until 3-4 years ago, everybody was using these G1 wafers, and now almost nobody is using them anymore. And in the next couple of years, these largest wafers, the M10 and G12, they will really start to dominate. And some people even expect that perhaps the wafer size will become even larger, but that is not so sure. Yeah. When we talk about these predictions of the ITR-PV roadmap, it's important to understand that, of course, these are predictions. There is no guarantee that it will really be like this, and nobody has a crystal ball. But this is, let's say, predictions based on the best knowledge of the PV industry itself at this moment. This is what they think will happen. Now, going to larger wafer sizes is very inconvenient in a certain way for everybody, not just for the industry, but also for research institutes, for instance, because you have to change or upgrade all your systems, because you are used to working with a certain wafer size, and all of a sudden you cannot get those wafers anymore. You have to use actually much larger wafers. So it's possible that your tools are not equipped, cannot be used for that. So then you have to, of course, invest in new tools or in upgrades of your tools. Then a second thing which is very important to note is that at this moment, almost the whole production of silicon photovoltaics is using monocrystalline silicon wafers. So until, let's say, 5 years ago, I think the majority of the solar cells made were based on multicrystalline silicon. And the reason was that multicrystalline silicon wafers were a lot cheaper than monocrystalline silicon wafers. And although the efficiency that you can achieve with multicrystalline silicon was lower, it was still competitive. But these days, there are two evolutions. First of all, the monocrystalline silicon wafers are almost the same price as multicrystalline, so you don't have a price difference anymore. And secondly, as I explained, the balance of system cost is becoming more and more important. So it's really important to lower the cost at system level to actually have high efficiency solar cells and modules. And this you can only achieve if you use monocrystalline silicon. So if you look to the situation in 2022, you see here the blue, that is actually P-type Czochralski silicon, so monosilicon. The orange, that is N-type Czochralski silicon. I will explain later why people are switching slowly from P-type to N-type. And the dark blue you see here, this is actually P and N-type multicrystalline. So it's only a few percent and it will completely fade out. That's the prediction by 2025. So the monosilicon wafers are dominating. At the moment, it's P-type, but the industry foresees that more and more N-type wafers will be used. And if finally also interesting to know, that's also changed in a very short time span. So if you look at these P-type monosilicon wafers, they are doped P-type by using gallium. So until 5 years ago, almost all wafers were doped by using boron. But if you use boron, we know that already for a long time, you have sometimes the possibility that you introduce so-called boron-oxygen complexes. This is a type of defect that can actually degrade a little bit your solar cell. It degrades the efficiency. And to avoid that, because we really want to have stable, high-efficiency solar cells, we now actually use gallium, which does not have this problem. So it is another example how the industry can very quickly completely change from one material to the other material to solve somehow a problem and to actually get a little bit cheaper or a little bit higher in efficiency. So now we have seen a little bit about how silicon wafers are made. So now we come to the next step, that is we're going to process the wafers into solar cells. So how is this typically done? So I will give a little bit historical explanation of how this was done and changing over time. So if we look back to 5 years ago or longer, then most of the solar cells that were being using this cell structure. And this is called the aluminium back surface field. So this is what you could call the first mass-produced crystalline silicon cell. It started being produced 15 years ago or so. And the cell structure is shown here. You typically have a P-type silicon wafer as a starting point, which can be multi or monocrystalline. Then at the front, you have an N-type emitter. So you have a P-N junction that you need to separate the electrons and the holes. The front surface is typically textured with random pyramids so that you have a lower reflection and a better lighting coupling. And then you have at the front a silicon nitride layer that acts as an anti-reflection coating and also as a passivation layer for the front surface. And of course, you also have metal contacts, typically silver at the front. And then at the rear, you have as a metal contact aluminium, and you have an aluminium silicon alloy that forms a back surface field. So this feature gives actually the name to the device type, namely aluminium BSF. Now, this is a relatively simple cell structure, but still you can reach relatively high efficiencies with it. So it was for many years very successful in the industry, especially because it's also very easy to process. You don't need a lot of process steps, which makes it, of course, very interesting for industry to mass produce. So typically, you need to texture the wafer. That's one step you have to do. You have to diffuse phosphor inside of the wafer at the front so that you have the PN junction. Now the phosphor is also typically diffused at the sides and partially also at the rear. So there you have to remove it again. That's the parasitic junction removal. Then you grow by plasma enhanced CVD, you grow the silicon nitride layer at the front. And then we use screen printing of silver metal at the front and aluminium metal at the rear. And then you do a high temperature firing step. So you put the hole into a furnace at high temperatures for a short time so that you actually form on the front and the rear, you form very good ohmic contacts. And also during this high temperature firing step, you form this aluminium silicon alloy, the aluminium back surface field. So this is what was done, let's say 10 years ago or longer. And so for many years, the industry used this process to make cells. And I show you here some data that comes from the production of such cells in the company Hanwha Q Cells. So this is like a German Korean company that was producing these cells in Germany. And they started the production. So these are not lab cells. These are data average cell conversion efficiencies coming from large batches from the production. So they started in 2010 with this cell concept. And in the beginning, they made average efficiencies of around 17%. And then over 3 or 4 years time, they increased this step by step to around 20%. How did they increase the efficiency? They just optimized the process. They started using better materials, for instance, better wafers and so on. So they optimized step by step everything they could. And that went pretty linearly. So you can more or less discern here an increase of 0.6% absolute per year. But at some point, the efficiency stagnated. So it seems you cannot really go above 20% with this cell concept. So it's not only in this company, of course, also in other companies, we see that. And the reason for that is that it's a simple cell concept. It's pretty good. You can already reach 20% efficiency, but if you want to go higher, then you actually bump into a big problem. That is actually that at the rear of the device, the whole silicon is in direct contact with the aluminium. And so you have a lot of recombination. So a lot of the minority carriers here will actually recombine at this rear surface. So basically, the name of the device, aluminium back surface field, is actually also the weak point of the device. And if you want to go to higher efficiencies than 20%, you can do whatever you want for on the other parts of the device. This thing will really be the dominating loss. So you really have to solve this rear surface passivation problem. And this is what we of course have done in the meantime. So in the meantime, if you look to the industry, I think almost nobody is producing these aluminium BSF cells anymore. Everybody is now producing so-called PERC cells. And a PERC cell stands for a passivated emitter and rear contact cell. And I just compare the cell structures here. So basically the front of the device is more or less identical. The difference is at the rear. So in the case of the aluminium BSF, we had the silicon surface was completely covered by aluminium everywhere. But in the PERC cell now, we have actually inserted this blue layer, which is a dielectric layer typically, that serves as a passivation layer. We have inserted this dielectric passivation layer between the aluminium and the silicon. But of course, we still need to have metal contacts, ohmic contacts. So a few percent of the surface is still in contact with the silicon. So we make local openings in the dielectric for a few percent of the surface area so that we can have local metal contacts. And this actually solves a lot of this problem that we have in the aluminium BSF cell of the rear surface recombination losses. Of course, this cell structure is a little bit more complicated, and to produce it in the industry, you need 2 extra steps. You need to grow the passivation layer or deposit it or somehow on the rear surface. And then you have to make these local contact openings through the dielectric, which is typically done by laser. So that means you need extra equipment, you need 2 extra steps in your production process. So you will have a higher cost, but the higher cost is no problem because we also have a much higher efficiency. And this is shown again here in the data of the Hanwha Q-cells factory. So the black dots I showed you before, this is the evolution of the aluminium BSF cells, which stabilize around 20%. And somewhere around 2014, the company then also started producing in their line the PERC cells. Okay, they call it here quantum. That is just the name that they give to their PERC cell concept. And you see that with these PERC cells, they reached a much higher efficiencies, above 23% at some point. And you see they could actually continue this increasing slope of around 0.5 to 0.6% absolute increase in their production efficiencies. And in the meantime, for these PERC cells, typically efficiencies around 24.5% have already been reached by several companies and so on. So it's way higher than what we can do with the aluminium BSF. Now, the question is, of course, how high can we go with these PERC cells? Because also the PERC cells are limited. And the funny thing in the end is that the main limitation of the PERC cell is still the surface recombination at the rear. Although we have only a few percent of the surface of the silicon in direct contact with the aluminium, at some point when you are above 24%, this becomes really a problem. And this is a graph that you will see coming back. So it's a kind of roadmap for the industry or for the different cell concepts that was made several years ago by Fraunhofer ISE. So what this map shows is that the average cell conversion efficiency in the industry is foreseen for aluminium BSF to sort of stabilize around 20%. And for PERC, the prediction is that probably we can go close to 24% with average cell efficiencies in industry. So these are not champion cells. Champion cells can be higher, but in industry. And so what is now limiting us to 24% here? It's really these recombination losses we have at the metal contacts still. So, but we already have good ideas, and I will show it. We have good results that show how we can actually go even higher. There are different things there. the most important part is we should go to passivating contacts. So these are contacts where actually we have nowhere direct contact between the silicon and the metal. Also, we probably have to switch from P-type wafers, which are typically used for both aluminium BSF and PERC, to N-type silicon wafers, because N-type silicon wafers, they have typically higher minority carrier lifetime, so they are better suited for the very high efficiency devices. And so I will show you now two examples that are being heavily investigated in silicon photovoltaics of passivated contact cells. The first one is the so-called heterojunction cell. So this is like a completely different cell concept than what we have seen before. So here you typically have an N-type silicon wafer. And the N-type silicon surfaces, both the front and the rear, are passivated by very thin intrinsic amorphous silicon layers. And then to form an emitter or a back surface field, very thin doped layers of either amorphous silicon or something else like nanocrystalline silicon oxide are used. And then we have on both sides a transparent conductive oxide for lateral transport. And then we have, of course, the metallization. And this is an example of a passivated contact because there is nowhere any direct contact between the metal on the front or the rear and the silicon. We always have these amorphous silicon layers and the TCO in between. So yeah, this summarizes what I was already saying before. So this is an example of passivated contacts and carrier selective contacts. It was originally developed by a Japanese company, Sanyo, that was later taken over by Panasonic. And at present, the highest efficiency quite recently obtained with this type of device was by the Chinese company Longi. They have reached on a large wafer an efficiency of 26.8%. And this is actually the world record efficiency currently for a single junction crystalline silicon. So this is the best silicon solar cell we have ever made. It's 26.8%. So it's quite a lot. And you see clearly higher than what we can achieve with the PERC cell. A second more conventional passivated contact cell concept is called TOPCon. It's actually, there are different names for it. TOPCon is the name that was given by Fraunhofer ISE. TOPCon stands for tunnel oxide passivated contact. So this cell concept again uses N-type silicon, but it looks more similar to the aluminium BSF and the PERC cells that we have seen before. So, okay, the front is similar to the PERC cell, but the main differences are at the rear. So typically at the rear, we have the rear of the silicon is passivated with a thin oxide layer. We call it a tunnel oxide because the current has to tunnel through it. And then on top of that oxide, we have a doped silicon thin film, typically a doped polysilicon film that actually gives you a surface field. And this is also an example of a passivated contact, which is carrier selective. So the tunnel oxide is typically used for surface passivation, so to reduce the dangling bonds at the surface. And the doped polycrystalline silicon layer is then used for selectivity. So it was originally developed by Fraunhofer ISE, this cell concept, but of course many companies and many institutes have also made variations of this. And at the moment, the highest cell efficiency achieved for this type of cell is 26.7%. So it's very close to the 26.8 we saw. And this was also achieved on large wafers and achieved by a Chinese company, in this case, Jollywood. So you see, the heterojunction and the TOPCon cell, they both lead to efficiencies almost of 27%, but these are, of course, the champion cells from the lab. So if we go back to the roadmap, we see that with passivating contacts, we can make a next step. We can probably reach in industry for mass production efficiencies of around 25%. Of course, again, every cell concept will have its particular limitations, but it becomes tougher and tougher to overcome those limitations. So here, one of the limitations is that we might have still quite a lot of optical losses, so-called parasitic absorption losses. And to overcome that, the next step could be to go to back junction solar cells. And here I give the example. There are different examples. I give one example of a back junction cell, which is a heterojunction IBC cell. The IBC stands for interdigitated back contacts. So in this case, we have an N-type silicon wafer. We have some front side passivation, but there is no metal contact this time at the front. All the metal contacts, the negative and the positive polarity, they're all at the rear. And in this case, yeah, it's a heterojunction cell. So again, we have these very thin amorphous silicon layers to passivate the front and the rear. So the emitter and the back surface field regions are at the rear, in this case made by amorphous silicon. Also, all the contacts are at the rear. So what does it mean? We have less shadowing losses at the front. So typically we have less parasitic absorption losses, so we have a higher current. But you can immediately see there is one big disadvantage. You have to sort of structure this cell at the rear. So it has a much more complicated processing, which is more difficult to, you can achieve it, of course, for instance, with lithography in the lab quite easily, but it's very difficult to do that in mass production in a very efficient, controlled way. So it will probably increase the cost quite a lot. The best cell achieved here is again in the same ballpark range of 26.7%, but this was already achieved actually 6 years ago by the Japanese company Kaneka. And in principle, we have here the potential of even going above 27%. So it's just a question of time before somebody reaches a higher efficiency with this type of cell. So this brings us then again to this roadmap. So we think that in mass production with passivating contacts at the rear of the device, so in a back contact device, we should be able in industry to produce on average 26% cells. Of course, not yet today. It still needs some time in the future, but this should be possible. And then, of course, you can still try to further increase it, but it will become very, very difficult. And I will explain that later in another section. To even go higher than this in efficiency, we will really need to completely rethink our strategy, and we will have to go for so-called tandem devices. But this I will explain later. So now, again, I will show you a few of the evolutions that are expected. So first, I've shown you many different cell concepts. So what is the industry now producing? So if you look to 2022, we see that almost all cells that are being produced are this orange. So these are the P-type PERC cells. So P-type PERC is really dominating, is the main technology that is being produced at this moment. More than 70% of the market is P-type PERC. You still see here this dark blue, a few percent of back surface field. So aluminium back surface field has not completely disappeared yet, but after 2023, the industry predicts that it will completely fade out because efficiencies are too low. It's not cost efficient anymore. Then you see already today, some of the passivated contacts are being produced. So you have 10% of TOPCon, a few percent of silicon heterojunction. And we see that the prediction is that these TOPCon and silicon heterojunction devices will slowly start taking over and get more and more market share. You also have the back contact cells, the IBC cells, but these are still very small today. And actually the industry believes also that this will remain a type of niche product. The reason for that is that probably you can go a little bit higher in efficiency with IBC, but it will come at a very high cost and a very large complexity to produce it. So it might not be cost efficient, but it might still be a very interesting cell concept for specific applications. Now, when they say here niche, we have to always keep in mind that the market, the total market, the amount of PV modules produced is each year increasing enormously. So if at some point we have a very large, let's say several terawatt of production, then even a few percent of production, it's still a very large volume. So it's still worthwhile to produce. Then we can also look at the cell efficiencies that we have now in mass production. So these are, let's say, the best cell efficiencies in mass production currently. So if we look to PERC cells, we are around 23.5%. So these are the best in class efficiencies. For TOPCon and silicon heterojunction, we are actually a little bit higher, already above 24%. So the prediction of the industry is that all these cell efficiencies in industry in the next 10 years will be substantially increased. And for the passivated contacts, yeah, we will probably reach 25 or 26%. So it's even higher than what we predicted in the past in this roadmap. And for the tandems, of course, which I will explain later, these are still being developed. They are not in mass production yet. But in the long run, the idea is there that this will allow us to go even much higher in efficiency. So silicon tandems are really the way forward, also how the industry sees it. These single junction efficiencies for silicon, close to 26%, that's really more or less the practical limit of what we can achieve. And that's why we need these silicon tandems to even go further than that. So now we have seen actually different cell concepts. Now I will say a few words how these cells are interconnected and laminated into a module. Of course, there are many different module processes. I will focus here only on, let's say, the standard process, and I will give a few extra, I will show a few extra things which are done. So I will focus here on two-side contacted solar cells. So that means you have a metal contact at the front and at the rear, and how these in standard PV modules are interconnected. So just to remind you, this is how the front and the rear of the solar cell looks like. At the front, we have silver. We have these fingers, which are connected by bus bars, which are solderable. And at the rear, we typically have the whole rear of the wafer is covered by aluminium, but typically you also have some silver bus bars there for solderability. Of course, in reality, especially now that we have these very large wafers, the actual design of these grids can vary from cell to cell. And here I show you only 2 bus bars. In reality, most cells that are produced now, they have much more bus bars, like 5 or even 9 or 12. It depends on the technology, but the principle is of course always the same. So how are we now going to interconnect these wafers? So you see here the first wafer, the front of the wafer, 2 bus bars, and we are going to solder on top of these bus bars so-called copper ribbons. These ribbons are made from copper. They are typically a few millimeters wide. They are a few hundred micrometers thick, and they have a coating which makes them solderable. So these steps, these copper ribbons are soldered on top of the contacts of the first cell, so at the front. We call this process, by the way, tabbing stringing. And then we take a second cell, and these same copper ribbons are now soldered to the rear contacts of the second cell. So in this way, we have connected the front polarity of the first cell with the rear polarity of the second cell. So these 2 cells will now be in series. They will be connected in series. And of course, we can continue like this. We can now connect the second cell with a third cell and so on. And of course, we have here an interplay between resistivity and optics. So from a resistivity point of view, it would be better to have more bus bars and wider bus bars so that you lower the resistivity of the contacts. But from an optical point of view, everywhere where you have a bus bar, you actually lose light that cannot enter the device. So from an optical point of view, you want to have as little bus bars as possible and as small bus bars as possible. Of course, there are tricks. Sometimes these ribbons are made in such a way that they can reflect some of the light, which then still can enter the cell somewhere else. So now let's see how we actually make the module assembly. So what is the layout of the traditional module? So we start with the module glass. So you start with a glass, which typically has a thickness of 3 millimeter and needs to be very transparent. So this will be the front of the module in the end. On top of that glass, we put an encapsulant to protect actually the cells against moisture ingress and other things. The encapsulant traditionally is made of EVA, it's a specific material, but there are many other materials being used at present already. And then we are going to put a string of cells on top of this encapsulant. So in this example, I give the example of the traditional 60 cell module. So it will be a module that consists of 60 cells. And you see here one string of 10 cells, which have been soldered together. So these are 10 cells, which are all connected in series. And we put 6 of these strings next to each other. So in total, this is 6 times 10, 60 cells. Then we are going in the next step, we are going to connect these 60 cells, these 6 strings, by large copper tabs. We call that actually bussing. So after this is done, we basically have 60 cells, and these 60 cells are all series connected. So it's one big snake, you could call it, of cells that are in series connected. Then we put also on the other side an encapsulant. So our 60 cells are now sandwiched between 2 layers of encapsulant. We of course have to make sure that we can get the current out of this, so we have some connection through the encapsulant with the outside world. For further protection at the rear, we put a backsheet. So this backsheet is typically consisting of different materials. It's again to protect against moisture ingress, oxygen, etc. You can have different backsheets. You can have a white backsheet for reflection. You can also have a transparent backsheet if you want to have a bifacial module. So there are different variations. Then the junction box is placed with output cables and a bypass diodes. And finally, of course, yeah, what I forgot to say before this, we have to laminate everything together. And so once the backsheet is there, it's put into a laminator so that everything is fixed. And then, of course, many of the modules, they still have an aluminum frame around it for further protection. So this is actually how the cells are interconnected and then laminated together into a PV module. So this is a classical process. There are, of course, many variations on this. If you, for instance, use back contact cells, you have to, of course, use a different approach. I will now, for 2-side contacted cells, give you a few of the alternatives. So one alternative is what is called multi-busbar soldering. It's actually more or less the same as what I've shown you, but because we have now very large wafers, often these wafers have, let's say, 9 to 12 bus bars, but the bus bars are very, very narrow. Otherwise, we lose too much light. And then you have to use very narrow wires or very narrow ribbons, but the principle is more or less the same. So this is done a lot. Another alternative is, instead of soldering, you can also use electrical conductive adhesives. So gluing, we glue instead of we solder the ribbons to the bus bars. And this is, for instance, interesting for heterojunction cells, which cannot withstand very high temperatures because high temperatures damage the cells. So there you perhaps don't want to go to high temperature soldering, but you can use these electrically conductive adhesives to glue the ribbons. Another approach, which is completely different, is so-called shingling. So in shingling, we actually cut the cell into elongated strips, and then the interconnection is not done via these copper ribbons, but it's done like the shingles on a roof. So we connect one shingle on the side with the next shingle. So you have a small overlap of 1 millimeter, let's say, between neighboring shingles. And this leads actually to very close packing, and also leads to a much better look. So the aesthetics are better. So for instance, for building integrated applications, this is really nice. And then something else which is also being done is so-called multi-wire technology, for instance, like Meyer Burger is doing. So here you don't need bus bars on the cells, but you just have the fingers. You actually use then a foil which contains wires to actually interconnect neighboring cells. And again, that gives a very, let's say, that gives a very nice look. So it's a very even look. You don't see the bus bars and the copper ribbons anymore because they are not there. So again, it gives a great aesthetics, and it also saves some silver. So it's a very interesting approach. Now, some evolution in the modules. So also here, the module size has increased a lot because, of course, the wafers have been increased. So if you make a 60-cell module with wafers of 156 millimeter, or you make a 60-cell module with wafers of 210 millimeter, it's going to be a huge difference. So where in the past, PV modules were typically 1 meter wide and perhaps 1.6, 1.7 meter long, we now see actually modules which are much longer, let's say 2.4 meters long, and also much wider because they use the much larger cells. And that also means that the not only the efficiency, of course, of modules has increased, but especially because of the size, the output of the modules has really drastically increased. So in the past, we had typically modules with, let's say, 400 watts power, but now these largest modules, they can easily have up to 700 watts of power for just one single module. But of course, these very large modules, they become very heavy. So probably we cannot make the modules much larger than this anymore, because then they become too heavy and it becomes very difficult to handle, etc. So one thing that I should also mention is that because we now use very large wafers, such a large wafer is actually generating a very large current. And this is not so good because the current that is generated by the cell needs to be transported to the outside world. And if you have a very large current, you might have a lot of resistive losses. So that's why you see most of the modules that are made today, they are actually based on so-called half cells. So what is done? The large wafer is made into a solar cell, but then before the solar cells are put into the modules, they are cut in two half cells. And the half cell, of course, produces only half of the current. And this is a big advantage. So you still have the same amount of cells in your module, but by cutting them in half, you actually reduce the current by a factor of 2, and you gain a lot in efficiency, and because you have much less resistive losses. And in the future, it's even expected that cells will be cut even in smaller parts, which is already done for the shingling technology, by the way. And then finally, the module efficiencies. So these are, again, the best-in-class module efficiencies that we have today. We see for PERC, we are around 21.5% module efficiency. For the passivated contacts, it's above 22%, and the highest module efficiencies are typically for the IBC modules, for instance, the SunPower ones, which have efficiencies of even close to 23%. Again, in the next 10 years, a lot of progress is expected for all the technologies. But in the end, the module efficiencies for single junction devices will be limited to 24.5%, perhaps 25%. If we want to go higher than that, again, we will need to go to silicon tandems. Now, I've mentioned these silicon tandems many times, so now I will now explain what we mean by that. So if we go back to a single junction silicon solar cell, we can actually calculate that the theoretical efficiency limit of such a device is 29.4%, more or less. So what does that mean? It means theoretically, we can never make a solar cell, a single junction silicon solar cell that has a higher efficiency than 29.4%. And of course, practically speaking, it will also be impossible to reach this 29.4%. So the practical limit is probably 27 point something even. Now 29.4% as such is not so very high, I would say. So why is this? So the reason is that we lose a lot of the energy of the incoming light, and it is because we have spectral mismatch. So silicon has a band gap of 1.1 eV. So that means that all the photons that are incoming, which have energy below the band gap, they cannot be absorbed. So this is this part of the spectrum that is already completely lost, but it's difficult to do something about that part. But even the photons that do have high enough energy to get absorbed, there also in the end, we use only part of that energy, the red part, and all the gray part is lost. Why is that? If you have, for instance, a blue photon that is absorbed, it will create an electron hole pair. So an electron is excited into the conduction band, it has a pretty high energy, but it will lose almost instantaneously a lot of that energy by thermalization losses, so in the form of heat, and it will actually relax to a lower energy state in the conduction band. And so this is the reason why we lose all this gray area here. So we can then go back to this map and we can wonder, okay, what happens if we have reached the practical limit for silicon single junction devices? Do we then simply have to stop? Do we have to look for a new material? How can we go on beyond this? So is this limit actually the end of the silicon solar cell technology? And the answer is no, it's not the end, because we can go to tandem, silicon-based tandems. So a crystalline silicon-based tandem or a multi-junction will allow to push the efficiencies above 30%. So what is the idea behind it? We're going to use a silicon solar cell and we are going to place another cell on top of that. And this top cell needs to have a higher band gap. And then what will happen is the light will first enter the top cell, and the high energy photons, let's say the blue light and so on, will be absorbed in this top cell. And the light with lower energy will actually go through the top cell and will be absorbed in the silicon bottom cell. So everything which is absorbed in the silicon bottom cell here in red is more or less the same as what we have here. But the blue light, so the high energy photons that are absorbed in the top cell, there actually, because the band gap of this material is higher, we will use more of their energy. So we lose less. The gray area here is smaller than what we have here. And this will allow in the end to have such a two cells on top of each other, which we call a tandem, to have a tandem device that has a higher efficiency. And we can calculate what are the theoretical efficiency limits for such tandems. And then it depends strongly on the band gap of the materials. So you have to select two materials to put on top of each other, which have matching band gaps. And we see then, this is an efficiency plot for such a tandem as a function of the top cell and the bottom cell band gap. We see that actually theoretically, we can reach even efficiencies up to 44%. So it's much higher than the 29% that we saw before. But you have to choose the right band gap materials. So the bottom cell typically needs to have a band gap between 0.9 and 1.1 EV. So that's good news because silicon has 1.1 EV, so it's a good bottom cell. And then for the top cell, you need a band gap typically of around 1.6 to 1.7 EV. And there we have different candidates. But of course, you need other requirements for this top cell. So you don't only need to have the right band gap, but you should also have a high efficiency, of course. And you should have minimal sub-band gap absorption. So that means that all the light that is not absorbed in the top cell, because it doesn't have enough energy, should actually be able to pass freely to the top cell and reach the bottom cell without any parasitic absorption. And then it turns out that this new material that has been studied since several years now in photovoltaics called perovskite seemed to be the ideal candidate. So I will not go into detail in these perovskite materials. I will just show you on this slide a little bit the basics behind it. So these perovskite materials are a kind of hybrid organic-inorganic material that has become really very popular in PV because in a very short time we have been able, after the discovery of this material, to make very highly efficient solar cells with it. We call it a perovskite material because it has a typical perovskite structure. So there are many materials that have a perovskite structure. The perovskite structure is typically a cube lattice, as is shown here. And you typically have a chemical formula of ABX3. So there are magnetic perovskite, there are superconducting perovskites, there are ferroelectric perovskites. You have a lot of different perovskite materials with different properties. Here we are talking about photovoltaic perovskites, and there typically the A ions are actually the organic material. So they are single or mixed cations of, for instance, metal ammonium. So this structure. Then you have a metal cation, the B material in the center, which is typically for the best devices lead, but it can also be tin. And then the X elements are, in our case, iodine, bromide, or chloride. Now, what are some of the features that make this material very successful? First of all, you can actually fabricate it very simple. Typically, solution-based processes are possible, also possible by, you can grow it by thermal co-evaporation. So that means actually that you have inexpensive ways of growing the material. Moreover, you don't need a lot of the material. You need only 100 nanometers to make a good device. And it's an inexpensive material consisting of abundant materials. So this makes it actually very interesting from a cost perspective. Moreover, it has a tunable band gap, as is shown here. So by changing the composition, you can change the band gap. And it typically leads to very high VOCs. And many research groups have already achieved efficiencies above 25%, which is really quite impressive for a single junction device. So all of this makes it a very interesting material to put on top of the silicon solar cells in tandems. Now, so the silicon and the perovskites can be combined in a tandem structure in different ways. So I show you here the three main architectures. The first one is called two-terminal approach. So in a two-terminal approach, you grow the top cell, so the perovskite, on top of the bottom cell. And we call it two-terminal because in the end, you will have, like in a regular single junction cell, you have a top contact and a back contact. So the positive side, the positive things about the two-terminal device is that it's a simple interconnection. You can just put this into a module and into a system as a normal single junction solar cell, but it has a few downsides. That is that you, of course, you have to grow the top cell on top of the bottom cell. So you might have some restrictions there. You don't want to damage the bottom cell. And you might not have all the freedoms to grow the top cell as you would like because you have limitations coming from the bottom cell. And finally, also, the two cells are series connected. So you need to have current matching. And of course, in real life, we know that the spectrum of the light is changing continuously over the day, over the seasons. So this is not so easy to deal with. So then on the other side, you have four-terminal devices. And in a four-terminal device, you actually grow the top cell and the bottom cell independent from each other. And then you just mechanically stack them on top of each other. So the advantage here is that you have independent fabrication and optimization of the two cells. So you have no limitations there. They are also not in series connected. So you don't care about current matching or spectral variation. So it doesn't matter if the both cells have a different current. But it's called four-terminal because you basically have two devices on top of each other, and each device has a top and a bottom contact. So you have four contacts in total. So that means to put it into a module, it's much more complicated and you need more power electronics, which can make it more expensive. And of course, you have to put these two on top of each other. You need to have some optical coupling layer. And typically, this can also lead to more optical losses, more parasitic absorption. And then there is a middle way, of course, where we actually do three terminals. So here you still have a monolithic device like the two-terminal. You grow the top cell on top of the bottom cell. But now you have not just a top contact and a bottom contact, you have a second bottom contact for the bottom cell. And this allows actually to also, in case you don't have current matching, because the two devices are in principle in series connected, but if you don't have current matching, you don't lose part of the current. You can actually extract it via this third contact. But again, you have three contacts here, so it means it's much more complicated to interconnect the cells. And of course, you still have to grow the top cell on top of the bottom cell, and the bottom cell also is more complicated. So, but these are three different approaches. The jury is still out there, so all three are being developed. We don't know yet if one of these is really much better than the other, so this is something that time will tell. But we really believe that the silicon-based tandems are the way forward for the silicon solar cell technology. And this will in the end allow us to go well above this 26% and hopefully also above 30%. And some recent results are shown here. For perovskite silicon tandems, not so long ago, a new world record was set of 33.7%. So this is much higher than the 26.8 record for single junction silicon. So it shows you can go much higher in efficiency. So this was obtained by researchers in KAUST in Saudi Arabia. A Chinese company, Longi, on commercial CZ silicon wafers has also reached a very high efficiency, 33.5%. And before the world record of KAUST, actually HZB in Berlin also had a world record of 32.5%. So it shows you many groups are getting a really very high efficiency, and almost monthly we see higher efficiencies. Now, in principle, we can also use other materials than perovskite as the top cell. For instance, we could go to 3,5 based tandems, where also very high efficiencies can be reached. But of course, 3,5 materials are typically quite expensive. So that brings me then to the final part, where I will say a few words about the challenges that we face for sustainable manufacturing at terawatt scale. So what is this about? So we have seen that in 2022, we have reached this milestone of 1 terawatt of PV modules worldwide installed. But if we want to become climate neutral by 2050, we need much more than 1 terawatt. How much exactly we need in terms of PV? It depends a little bit on the assumptions that you take. So there are different models, but typically we can say, like in this model, that we probably need around 50 to 60 times more of PV installed and operational than what we have today. So if we want to achieve 50 or 60 terawatt peak of PV modules by 2050, we only have 30 years left or even less. And that means that per year from now on, we should start producing more than 1 terawatt peak, 1 to 3 terawatt peak per year to actually achieve this 60 or 50, 60 terawatt installed. Now in 2022, we have only made 250 to 300. So the exact number is not so clear, but we are far below what we need to install year by year to reach these numbers. So that means the annual production needs to increase probably by a factor of 10 in the coming years and decades. And this is very challenging, especially from a material point of view. And this is shown here. So if we go to 2021, we can say that we produced around 180 gigawatt of PERC solar cells. And here you see, this is taken from this paper, the materials, the quantity of materials that were needed for this 180 gigawatt PERC production. So we have steel, we have concrete, that is just for the mounting structures of the systems. We have glass, of course, we have aluminum, we have copper, we have polysilicon and the silicon material itself, and we have silver. So you see here in absolute value, the amount of tons of material that we needed for 180 gigawatts of PERC installations. And you see also then in percentage, how much this material, in percentage, how much of the worldwide production of this material was needed for 180 gigawatts. And the main bottleneck is actually the silver. So we use only a few grams of silver per module, but because we produce almost 1 billion modules, this is actually a very large number. And for this 180 gigawatt of PERC, it already corresponded to 8% of the worldwide production. Now, if we want to produce 1 terawatt of these materials, which is the minimum we will have to do, it's roughly 5 times more. So we need 5 times more of all these materials, which for silver would mean that we already are around 43% of the worldwide production. So yeah, these become really mind-blowing numbers, actually, if you see what is needed. And this is really potentially a problem. So if we look into these materials in more detail, so we have copper, aluminum, glass, steel, and concrete. Yes, we need a lot of materials in volume. We need a lot. but actually these are not showstoppers. There is actually enough material there for us for this 1 terawatt to produce. If we look to the polysilicon, at the moment, most of the silicon that is actually produced worldwide is already used for photovoltaics. Now we know that silicon is a very abundant material, so there is in principle not a problem to really upscale the production. It's just a question, there is no material scarcity, it's just a question of having more polysilicon factories, let's call it. So for PERC, we know that we need around 2,000 tons of polysilicon to make 1 gigawatt of PERC modules. And so if we have to go to terawatt production, yes, then we need many more factories for polysilicon, but actually this is feasible. So silicon is also not really a critical material. Moreover, the industry is still further working on reducing the amount of polysilicon that we need per gigawatt. So they predict that the consumption will decrease by 30% in the next 10 years, which is of course also good news from an energy point of view and from a cost point of view. But the main critical material that I want to highlight here today is actually silver. And so here you see in red, so this is a curve that shows the material consumption of silver as tons per gigawatt. So we see, we have to assume that the silver production worldwide will not increase substantially in the next years and decades. So we assume the silver production stays stable. And we then have to assume that we cannot use all the silver that is being produced worldwide just for PV. That's never going to happen. It will also increase the price of silver enormously, which we cannot afford. So we assume that we have a maximum of, let's say, 20% of the worldwide silver that we can ever use for PV production. So then we can calculate if we have 1 terawatt per year of production, we have a limit of 6 ton of silver that we can use per gigawatt. If we want to produce 3 terawatt per year, then of course this is lowered by a factor of 3, and it's only 2 tons of silver per gigawatt. Now, the amount of silver that we actually need really depends on the different technologies. So you see here, the dark gray is actually at current the amount of silver that is used per gigawatt for PERC, for TOPCon, and for silicon heterojunction. And the light gray is actually the prediction of the industry of how much they will need by 2032. So by having some improvements. And we see that none of these technologies is actually reaching this low value. So we still have a lot of work to do. But PERC is typically doing much better at the moment, at least, than TOPCon and silicon heterojunction. So what the industry thinks about this, so they say the silver reduction will continue, but typically for N-type cells, we have more silver needed than for P-type. If we look to P-type PERC in 2022, we typically needed 11 tons per gigawatt of silver, whereas we should only use 6 or even 2. And 300 gigawatt per production in 2022 means that we used around 330 tons of silver, or corresponding to 10% of the total amount of silver produced that year. And cost-wise, the cost is also not negligible. So the silver that we use is costing us around 0.7 cent per watt. So that means it's 2 or 3%, let's say 3% of the total cost of the PV module. So we have seen 40% of the cost of the PV module is the silicon, and 3% of the cost is the silver. So the silver is also quite costly. So we cannot really increase the price of the silver too much, or otherwise we run into problems. So the main message that I have here then today is actually that silicon PV technology, which is considered by many people as a very mature technology because it has been very successful, it's produced in very large quantities, it leads to the lowest cost of electricity, but it's still not really ready yet for sustainable massive deployment that we need for the future. So we still need a lot of work from the point of view of materials. So I focused on silver, but actually the same is true for indium and bismuth consumption. We are still far above what we can afford if we want to have terawatt production. That makes it also very important that we recycle all the modules 100%, not just for the environment, of course, but also we really need the materials that are inside to produce the future PV modules. And so there is still lots of work to be done to actually become compatible with the multi-terawatt market. And especially we have to further reduce the amount of silver that we are using and also the amount of indium. So we should really try to get indium-free TCOs working properly. This is very important for the tandem concepts. And so although the industry predicts that the PERC solar cells will at some point be replaced in the production by TOPCon and or silicon heterojunction, it's possible that we will have to stay producing PERC for a much longer time because PERC at the moment is the most sustainable technology that we have. So from a sustainable point of view, PERC is actually doing better than the others. So this brings me to the summary of my presentation. So in 2022, we had a small party, I would say. So we surpassed a milestone basically. So we have installed now more than 1 terawatt of PV. So this is really nice. We see that single junction silicon solar cells are nearing their practical limit. And so we will need to go at some point to silicon-based tandems to surpass this practical limit and to be able on the long run to go to efficiencies above 30% in mass production. Now this 1 terawatt, as I said, is nice, but we probably need to have 50 times more in 30 years from now. And to do that, we really have to ramp up the mass production of silicon PV modules. But to be able to do that in a sustainable way will still require a lot of R&D work. But it should be doable. We just have to be aware of it, that we have to focus on this. And then finally, I would like to acknowledge many of my co-workers from different institutes that have provided some slides or some ideas for this presentation. And of course, I would like to thank you for your attention.
Okay, thank you very much, Ivan, for this very nice talk, which give really an overview of the state-of-the-art silicon solar cells from the first version of back surface field until the heterojunction. So the conference is open for the discussion, and I think if you need to talk, you have to ask for the micro or to raise your hand. If you don't, you can also write your questions in the chat. So please go ahead for the audience. Maybe I will open the chat to see some questions here before. So there is Dr. Adel Latif Bouaishi. He asked about the environment impact of the manufacturing of PERC photovoltaic cell versus the aluminum back surface field.
Yeah, so that's a good question. But yeah, as I've shown in my slides, at the moment, for instance, from the point of view of silver, PERC is actually doing pretty well. And I think if we compare, because back surface field is not anymore considered in these graphs, because basically it has already faded out. It's really the past. But if we compare aluminium BSF with PERC, I would say the PERC has a much higher efficiency. And because of this, actually, from an environmental point of view, because the cell concepts are pretty similar, so the amount of silver that you need to use and the wafer thickness and so on, it's all very similar. So from an environmental point of view, I think the PERC is for sure going to do much better than the aluminium BSF, because we consider everything from the point of view as how much you need of something and how much greenhouse gases you produce per watt or per gigawatt. And because actually the PERC cell has a much higher efficiency than the aluminium BSF, it's producing more watts, and it will use more or less the same materials, etc. So it will actually, from an environmental point of view, for sure do better. The problem now is that we have also cell concepts that can outperform PERC, like the TOPCon and the heterojunction cell. But there we actually see that from an environmental point of view, from a sustainability point of view, actually these are not really doing better yet than the PERC cell. So that means we have to put more effort now in not further increasing the efficiency of TOPCon and heterojunction, but lowering actually the environmental impact of these devices. Because if we don't do that, then it's nice that they have a higher efficiency, but we should not really replace PERC probably by them, because it will be bad for sustainability and environment.
Okay, thank you. The other questions is about the stability of the perovskite when it's integrated to the silicon. Do you think the perovskite now, which is very efficient, of course, it's stable enough to go to the technology?
Yeah, that's really the key question now that needs to be answered. And I was recently also at some events, workshops, etc., where this was the main conclusion. We have to really focus now on the stability of these systems. There are, of course, already companies like Oxford PV that claim that they have very stable materials, and we have seen many perovskite cells that surpass all kinds of IEC tests. But everybody understands, I think, that there is indeed at this moment still a stability issue. So perovskites seem a very promising material, not just for tandems, but also for single junction in certain applications. But we have to indeed get it more stable, and we have to prove that it can be really stable over 20, 30 years. And this is now the whole, let's say, perovskite community, but also the silicon community understands that this is now one of the main things to focus on. Will we be able to get it really as stable as we need to be? It's still an open question. So hopefully yes, because then we can really use the material. If not, we have to look for alternatives. So that's what I also always say. I didn't really say it here in the presentation, but everybody is focused on the perovskites now, but we should also look to alternatives, because if the perovskites in the end cannot be made stable, then we cannot use them. So we still need to also look into alternatives to be on the safe side.
Okay, that was the question from Paula or Saul. Now I want to ask one question about silver. I believe that silver will be a big problem because it's a very expensive and so on. And do you think about graphene? Can graphene, carbon, I mean, a form of carbon, can replace silver? Do you think it's possible?
Yeah, it's well, people that look to graphene are typically also looking to graphene perhaps to replace TCOs. Yes. Not so much as the metal itself. So I think the thing we are looking most at the moment to replace the silver completely or almost completely is actually copper. And there I think it's very realistic. I think for graphene, I'm not an expert on it, but I think there would still be lots of research needed. We should also not forget the question about the perovskite stability was really a relevant question, but it's the same for anything that we are going to use. So if we go use graphene, for instance, in silicon solar cells, it also, for instance, has to be proven that it would be stable for 25, 30 years. And with metals like copper and silver, we know that it can be stable. For graphene also, it still needs to be investigated. But I fully agree that silver is really the main problem for the silicon technology, and therefore getting rid of the silver completely would be the best. And this could be with copper, either copper via copper plating or also copper via copper paste, so with screen printing. So both ways are being also massively investigated.
Okay. Just one last question from me, and then I will give to the audience. You mentioned that now people are focusing on large area silicon to make a large angle and to cut it in slide, etc. And then you talk about to cut it again in half, third, and even more. What about from the beginning to make only a small diameter of silicon?
Yeah, of course. You would think that this would make more sense, but from a production point of view and a throughput point of view, it's better to actually process on the larger wafers. And also the larger wafers can be made cheaper than the smaller wafers. Okay. So it's all about cost. Now there is indeed one problem. So we have these large wafers, we process them into a solar cell, and then we have to cut it again. So when you cut it, the way you cut it has to be done very carefully because it can create all kinds of defects, also micro cracks, which actually will weaken the silicon. And also where you cut, you have no passivation at the edge anymore. So people are also looking at repassivation steps. So there are some disadvantages of cutting it, but these disadvantages, we can overcome them. And in the end, from a production point of view, it is still better to, from throughput reasons and so on, to process the large wafers. Should not forget also the amount of wafers that are produced per second, per hour is also always increasing. So nowadays, throughput of silicon PV production is typically 5,000 to even 10,000 wafers per hour that are being processed. So if you go again now to smaller wafers, as we have done in the past, not only will the making of these wafers be more expensive, but also to reach the same throughput, you need more machines, which makes it much more expensive. So it's really all about cost and throughput. That's the only reason that these large wafers are being used, and they will stay because, there is no way around it. If you use smaller wafers again from the start, which in a way would perhaps be more logical, you will have a much higher cost again.
Okay, thank you. So is there any questions from the audience? It's the time to ask if you have any questions about photovoltaics. So there is something here. Munir Abraham, if I spell his name correctly, you mentioned that the PV module should be manufactured in a way that makes them easily recyclable. I was wondering if the current manufacturers are actually taking this into account in the manufacturing process, and what are the techniques that are used or should be used for this purpose?
Yeah, it's a good question. So I would say at the moment, manufacturers are not taking this into account, but slowly the awareness is coming. And luckily, this is not only the problem that we have in photovoltaics, it's more a general problem. And so I think slowly the mindset will change, and we will actually take this into account. There are, of course, already manufacturers that do something similar. But so the main problem is that I've shown you how the module is fabricated. And so basically what we do is we put a stack of materials together and we laminate it. And actually we laminate it in such a way with these materials that we try that this is like impenetrable for anything like moisture and so on, and it will never come loose again. But then, and that is really needed to ensure that the PV module stays working properly when it's outside in the rain and the snow and the hail and so on. But then, of course, at some point in time, we want to recycle it and we have to actually, take everything apart. But these two things seem to be very incompatible because first we glue everything together in such a way that it can never be destroyed. We want to, destroy it or take it apart again in a simple way. So that's very difficult. But the good thing is, and I wasn't really aware of that myself so much, but I visited some companies recently this problem is being faced actually everywhere. And so you have the companies that make all these special glues and laminates and so on. They are doing now a lot of development to actually make new ways of gluing things together, where you can actually control in some way or another at some point in time, if you want to take it apart again, that it's possible. So I think from a material point of view, let's call it simply gluing things together, there is a lot of things in the pipeline. We will have a lot of new materials in the future that will probably, hopefully, allow us to still put things together in such a way that they stay together. But by doing something, I don't know, some kind of radiation, for instance, we can actually tune the material at some point in time that it releases again. So there are lots of stuff like that going on. And so that's really a question of material research. So we can perhaps at some point have different lamination materials and so on that are much easier at some point to take apart again. There are, of course, also already some companies in the past that didn't use lamination to put PV modules together, but use, for instance, vacuum. And then also it's easier to detach. So there are some ideas there, and time will tell what will be the best.
Okay.
And I think at the moment people do not yet consider it, because actually it's still very easy to get, or relatively easy and cheap to get the materials that you need. But in the future, it will become much more expensive and difficult to get certain materials. And then people will be very happy to design the modules in a different way so that they can actually reuse, because otherwise they will not be able to make the modules.
Okay, the side Qassu asked about the EVA ethyl vinyl acetate encapsulation, if it's good for a perovskite solar cell.
Yeah, I have to say that the EVA is also used less today for silicon than in the past. So there are lots of alternatives being developed. Because we are, even in silicon, we sometimes have problems with EVA, like discoloration and so on. So I'm not an expert actually on the encapsulation of perovskite solar cells. I know that at the moment, yeah, we still haven't found the right material to properly do it. So probably it's not going to be EVA, but yeah, I cannot really say because I don't know what in the end it will be.
Okay. So Hisham Sharifi asked about how thick and large are the bulk silicon-based solar cell? What we gain in one side, we lose in other side. So I don't understand the end of the sentence, but
yeah. So the solar cells that are typically made now in the industry, let's say they are roughly 180 micrometers thick, because we are going to. So the idea has always been that we should go also to thinner and thinner wafers to save silicon, but because we are going to larger wafers, we still have to make sure that these wafers are, mechanically stable. So that's why the thickness of the wafers has not really decreased the last year. So typically it's around 180 micrometers thickness. And I also don't really understand what we gain in one side, we lose it other side, down to 80 micron. So I'm not 100% sure what is meant here.
Me too. I don't know. I don't understand. Maybe he can ask again. But by the way, I want in. I hope Hisham Sharifi can put his sentences otherwise. But I want to know one thing. The terawatt, you are talking about how much terawatt we need by 2050. And of course, it's not very easy. It's not very trivial. But what about if we add the fact that it's possible to use CPV for silicon. I mean, instead of one sun, to use more than one sun. Is it possible to reduce a little bit the amount of terawatt like this?
Yeah, well, the amount of terawatt, of course, is open for discussion. There are different models that come to different values. So the 50, 60 terawatt that I showed here is taken from a model where they really assume that we have a very large electrification in the society. And so it could also be that in the end we have 30 or 40 terawatts and it's already sufficient. But anyway, the main message is that, yeah, it's many 10 times more than what we have today. So it will require a massive upscaling of our current production. Okay, if we use, of course, alternatives like CPV, yeah, you could cover some of the terawatts by this. But we should not forget, once you have, well, there is always the question, will it be cost effective? And we should also not forget, if you have CPV with concentrators, you cannot use it everywhere, you know? So it only works with direct light.
Yes.
Of course, I've been involved in a project now that's very interesting, where we actually try to combine CPV and PV together, so that you have actually a hybrid system where part of the light is concentrated and generates the thermal energy, and part of the light is actually going to a PV module. And with such a hybrid system, in case that you have, for instance, clouds, so diffuse light, you could actually completely operate in PV mode. So I think in the end, I mean, in all the models that I've seen, yeah, the focus is really on PV and not so much on CPV. So I think CPV has a role to play, but it will be much smaller than PV always. So the majority will still need to come from the PV. And on the other hand, of course, I don't know if we could, for instance, replace everything of PV by CPV, then we still might run into other problems that you need to produce all these optics and so on. And perhaps also we actually, the problems that we have, this is very important to understand, the problems that we have, the challenges, let's call it, that we have for PV, which are solvable, I believe. We are facing that with all the renewable energy technologies. For wind energy, it's exactly the same. For batteries, it's exactly the same. So we have this huge challenge, this energy system of the future. It has the huge challenge that, you know, resources are scarce and we have to deal somehow with that. But it's a big challenge, yes, but it's also a very big opportunity, in my view, to actually create, yeah, the economy of the future. You know, it will also create lots of jobs and so on. And it's a challenge, but it's really, also the economic opportunity of the future.
Yeah. Okay. So I don't know if there is anyone who want to ask any questions. Otherwise, I have my last questions. When we buy a car, for example, we don't care about the price. Some people, they can buy a car for 50,000 euro and so on. But why we care about the price for the energy and for the module? What is the reason for that? Because when we buy a car, then we can buy, a lot of people buy a very expensive car without thinking about the price. But when we talk about photovoltaics, we always consider the price as a first choose.
Yeah, that's a very good question, and I also wonder about it myself often. But I think the answer is simple. I mean, just because we as humans, we don't necessarily act rationally. We act more emotionally. So okay, people see a car as, you know, a nice thing, a status symbol, and so on. And so for something like that, you are willing to pay more. In fact, it's even worse than what you say, because I think if you are in the business of producing PV modules, it's very, very difficult to earn a profit.
Yes.
And so, whereas I think in the car industry, for instance, it's much easier. But if you think about it, PV modules and making batteries and so on, that's really crucial for our survival. So if this should be a business where, you know, you should be able to make money, you know, but it's not the case. So economics doesn't make often sense, because the businesses where you can make most of the money are actually things that in fact we don't really need, you know. It's luxury goods and so on. And the bare essentials, there it's really a struggle, you know, to make money, and it needs to be sometimes supported by government and so on. And that's really strange, because we focus on the wrong things. We give money to the wrong things, indeed.
Yes. Okay. Thank you very much. If there are other questions, you can just send it to me, and I can give it back to the speaker. Otherwise, I would like to thank you very much, Professor Evan Gordon, for this, for your time, for this very amazing talk, where I have the feeling I know everything now about the photovoltaic until 2023, and we hope to invite you again when there are some progress. Thank you very much.
Okay, thank you. It was really a pleasure of giving this presentation. And indeed, if you have any more questions, you can always contact me. I will be happy to answer them.
Okay, thank you very much. Thank you.